Welcome to our Compass seminar. Today's seminar is special. It's given by our department visitor, Dr. Michael Spall from the Spall Oceanographic Institution. Just a very quick background on Mike. Mike got his bachelor degree in mechanical engineering, right? And his PhD comes from Harvard University, 1988. Right? And he's been at the Spall Oceanographic Institution since 1990, right? Yes.
Yeah.
Okay. Michael, where should I start? He published over 100 papers, at least 100 papers in reviewed journals, and he had multiple editorial appointments. Most notably, he was the chief editor for JPO. So many of you at least know his name from that, if not from his wonderful papers. Mike interests are pretty wide. Most his work is focused on ocean dynamics, on variable scales, from AMAC to mesoscale, from large scale to regional, from ocean to air sea interaction. What else? Last time Michael visited Rasmus was in 1995.
I think so.
Something right. Still back then. Right. What else shall I add? Bigelow Chair for Excellence in Oceanography, and just multiple wonderful achievements in our field. So it's a pleasure to host Michael, and please go ahead.
Thank you. Thank you for having me. We'll have to make it less than 25 years or whatever it is next time. 22 years.
Yeah.
So yes, today I want to talk about sea ice in the Arctic Ocean. I'm new to sea ice. This is my first foray into the question, and it'll probably be evident in the talk that I'm kind of new to it. An advantage to that, because you can ask questions that people who've been working with sea ice for their whole careers, I think, didn't think to ask. And these are really my main questions. To me, sort of zero-thought questions if you want to understand sea ice in the Arctic. What determines its thickness, and what determines how much gets exported from the Arctic to the rest of the world? So, sea ice is, of course, a really important part for our climate system. It represents a significant source of fresh water to the Nordic seas and the subpolar gyre. It's roughly equivalent in magnitude to the liquid form of fresh water exported from the Arctic. We know that it can influence deep convection at lower latitudes. It affects, as a consequence of that, Earth sea exchange. The most famous example is the Great Salinity Anomaly. There have been others that weren't quite so great, but they're generally believed to be traced back to freshwater anomalies coming out of the Arctic Ocean. Within the Arctic, it modulates the heat exchange with the atmosphere because the albedo of ice or snow-covered ice is much higher than the albedo of open water. So the incoming solar radiation gets reflected back into the atmosphere. If you have ice, it gets absorbed into the ocean if you have water. Of course, there's a potential for positive feedback there because warmer water delays the onset of ice later in the winter, leads to longer periods of open water, more heat absorption, and so on. The ice actually drives the ocean circulation in the Arctic through stress transmitted from the bottom of the ice into the ocean. In regions of open water, the wind blows directly on the ocean. When you've got ice in between, it acts as a filter. And I'm going to talk a little bit about how ice modulates the wind stress, and so that the ocean sees something different than it would if the ice were not there. It's a source of salt and overturning, convection in the ocean from brine rejection. So when you form ice, ice doesn't retain salt very well, so most of that salt goes down into the ocean. It's dense because it's salty, results in deep convection, particularly on the shelves of the Arctic, and you see that water mass kind of convecting down into the deeper basin. And then finally, with regards to climate issues, there's evidence that ice cover in the Arctic Ocean affects mid-latitude storm tracks and temperatures and precipitation patterns. So sea ice in the Arctic is an important component to the global climate system. This is a polar projection of the Arctic. For orientation, Greenland's here. This is Fram Strait. Alaska sits over here, Canada. This is the mean spring ice thickness, and the vectors are the ice drift. The drift is dominated by two features: Beaufort gyre, which is this anicyclonic circulation over here, and the transpolar drift. So ice is kind of leaving the Russian shelves, transmitted across the North Pole towards Greenland and out Fram Strait. They're both generally believed to be wind-driven. There's been some recent work on the dynamics of the Beaufort gyre. I'm not going to talk about any of that today. I'm really going to focus on this transpolar drift. As far as the ice thickness goes, the colors here are thickness. It's about 5 meters over here by Canada and Greenland, and it's very thin, less than a meter over here on the Russian shelves. So that's kind of the big picture, and my goal today is to try to explain why it's thick over here and thin over here, and why the ice is kind of taking that trajectory. So this is the picture I just showed you. This is the mean surface pressure. These contours are high is over here, low is over here. So the geostrophic wind implied by these surface pressure contours is from Russia toward Greenland, and roughly uniform. These isobars are kind of parallel and roughly uniformly spaced. This is the Beaufort high. That's what's driving this anticyclonic circulation. The big picture is you kind of have wind blowing uniformly from the eastern hemisphere to the western hemisphere. But the ice, if you look carefully, you'll see that the ice is crossing to the left under the isobars in order to get out Fram Strait. So ice in free drift, we know, goes about 1 or 2% of the wind speed, and it goes about 25 degrees to the right of the wind. Ice here is going to the left of the wind. So that's our first clue that this is just not free ice flows that are getting blown out by the wind. Something else must be going on. So just a brief background. It's brief because there's a whole lot on these kinds of simple approaches. Background of ice drift. We consider a momentum budget. Wind, drag, Coriolis term, there's stress within the ice, and there's a sea surface tilt term. So the early efforts at building ice models considered subsets of these terms. These are some of the important early papers. You might recognize some names: Nansen, Sverdrup, Rossby, Montgomery. These are kind of giants in physical oceanography. They would consider subsets of these terms. Typically, they had to provide some information from observations. Sometimes the predictions from their equations matched observations, sometimes they didn't. In general, most of the ice drift was independent of ice thickness and independent of thermodynamics. So these were kind of incomplete systems. In the 70s, the understanding and representation of the ice dynamics was advanced with more complex ice rheologies. So the rheologies are relating the stress within the ice to ice shear and ice thickness. So that gives a more realistic ice rheology. The penalty for that is now your equations are coupled. So you've got a momentum equation where the stress depends on the velocity and the velocity shear, and it depends on the ice thickness. That brings in a thermodynamic equation, which also depends on the velocity and the cooling. So now we get really complicated systems of equations. They generally require numerical solutions. So those systems of equations have been put into coupled GCMs, ocean, ice, atmosphere, and they're useful for diagnosing things. You can run these models of the Arctic, you can diagnose the terms in a momentum budget, and infer which processes are important. It's different than understanding why they're then important or how they depend on parameters, but you can identify the dominant balances. You can also use them as sort of laboratories. What happens if the atmosphere warms? What happens if the wind blows strong? And you can diagnose what goes on. But these are fully coupled, nonlinear, complicated GCMs. So I haven't been able to find any simple analytic models or even any simple physical understanding for that basic pattern of ice drift and ice thickness. So that's my goal. Or the reason that I think we don't have one of those in hand is it's really complicated. Don't try to read this in any detail, but this is a representation of the thermodynamic balances in Arctic sea ice. This is ice thickness here in the middle. These other things are all sorts of things: snow depth, melt ponds, incoming radiation, cloud cover. And you can see by all the arrows, everything depends on everything else. So that's a mess. And that's just the thermodynamics. We also need to consider the mechanical forcing. The wind is blowing on the ice is rubbing against the ocean. You get convergence and ridging, you get divergence and leads. So the whole system's pretty complicated. I'm going to go after something much less ambitious. This is a schematic of my ice model. So I have a single slab of ice. Its thickness is a function of x and y, h. There's horizontal velocity, u and v, which are also a function of x and y. It sits over a motionless ocean at the freezing temperature. So there's no melt from below. I'm going to blow a wind on it, and I'm going to have a parameterization of heat exchange with the atmosphere. I'm going to assume that the ice concentration is 100%, so I have no divergences and leads opening up. I'm ignoring things like snow and melt ponds and salinity. I'm ignoring the Beaufort gyre, and I'm ignoring time dependence. All right, so I'm really just after just the most basic description I can come up with. So how about time dependence? We know there's a lot of time dependence in the Arctic. We know there's a strong seasonal cycle, and there's also interannual variability. So this is a plot of the sea ice extent and the sea ice volume. This is over a seasonal cycle, so you can see quite a strong variability. These each vary by about 50% over an annual cycle. You can also see or infer that there's low frequency variability. These colored lines in each of the graphs are recent years, 2018, 2017, 2016. And you see they tend to sit on the bottom of these graphs. So the ice extent and the ice volume has been decreasing over the satellite record, so since the late 70s. I would argue that the existence of the mean ice pattern and the ice drift is not because of the seasonal cycle. I expect it's certainly modified by the seasonal cycle, but I don't think it exists because of the seasonal cycle. So to keep things tractable and simple, I'm going to assume steady forcing. I'll show some results from a numerical model in which I have seasonal forcing, and I'll argue that the steady forcing represents most of the physics that's going on. But this is kind of what I'm ignoring. Okay, so we'll get into some of the nitty-gritty here. These are linear, steady ice momentum equations. My coordinate system is such that I have a long wind coordinate, so I have a wind stress. There's a Coriolis term. This is sea surface height tilt. There's internal stress, and there's ice ocean drag. I've defined my coordinates so that one of the coordinates is in the direction of the wind, and the other is perpendicular to that direction. So this one's just like that one, except there's no wind term. These are all the variables. They're pretty standard. What I'm going to be solving for is the thickness and the velocity. Okay, so the stress terms, these sigma terms here, are typically written like this. Okay, so they depend on bulk and shear viscosities, those are these betas and zetas. They depend on the strain field, this epsilon, which is the shear, the divergence in the shear and the horizontal velocity field. So that's pretty complicated to handle analytically. Couples the equations in a kind of messy way. P is the pressure term, and that depends on the sea ice concentration, that's the C term, and on the ice thickness. So I'm going to simplify this to what's called a cavitating fluid ice rheology. It's a fancy name for getting rid of everything except the last term here. And I'm going to assume that C is 1. So this exponential term drops out. So my stress is just proportional to P star, which is a constant, and the ice thickness, and then the Fraunhofer delta. So I'm ignoring the cross terms in the stress. So I have just two terms, one in each momentum equation. This cavitating fluid rheology has been put into GCMs and compared to this full viscous plastic rheology, and the basic patterns are the same. The differences in a quantitative sense are 15% or something like that. So I'm willing to accept a 15% error given all the other stuff I'm going to do. So that's my stress tensor. It's just proportional to the ice thickness. So my ice does not resist shear, and it doesn't resist divergence. It just resists compression. Okay, so now we are going to consider a continuity equation. So the horizontal flux divergence of ice thickness here is balanced by a heat loss to the atmosphere Q. I'm going to represent this Q as some constant over H. H is the thickness of the ice. So that's equivalent to assuming that the linear temperature profile through the ice is linear. I'm going to assume it's freezing temperature at the bottom of the ice. It's some specified boundary condition at the top of the ice. I'm specifying the surface temperature of the ice, and it's just conducted through by a thermal conductivity. I'm igniting ice melt from below. So I can test that, this relationship, that Q goes like 1 over H. I'm going to talk a little bit later about a general circulation model, but I ran one that has ice on it, and I diagnosed the heat flux against the ice thickness. These colors here are the area in the model that has this heat flux ice thickness representation, and the red line is 30 over H. 30 is the thermal conductivity times the change in temperature, which in this case is about 2 and 15. So, comparison isn't perfect. I get a little more heat flux for thick ice and a little less for thin ice, but by and large, that looks pretty good, roughly a 1 over H dependence. Okay, so that's my heat flux parameterization. This is my continuity equation. Now, another important assumption, I'm going to assume that the ice thickness varies much more rapidly in the direction of the wind than it does perpendicular to the wind. So in this coordinate system, I'm going to assume that the thickness varies in this direction much faster than it does in this direction. And it's not too bad of an assumption. Maybe it's not great way over here, but it's pretty good here. So in terms of my coordinate systems, I'm assuming d by dy is much less than d by dx. So I can write that in terms of this small parameter epsilon. d by dy is order epsilon d by dx. Turns out this is a key assumption that's going to allow for analytic progress, because it allows me to pull apart the equations a little bit. Okay, so now in non-dimensional, it's my continuity equation. Now this epsilon shows up because that's d by dy. So this term is small. Gamma is the non-dimensional version of that heat exchange. It's defined right here. Gamma is an order 1 constant. Epsilon is small. So there's two possible limits here. If H is order 1, and I've scaled H up here. I'll explain why I chose that scaling in a bit. But if H is order 1, in order for this equation to balance, U has to be order 1, because gamma is order 1. Right? But if H is really small, H is much less than 1, then U has to be much greater than 1 in order to satisfy the continuity equation. Right? Now, over most of the Arctic, I'm expecting H to be order 1, but right where the water flows into the Arctic, along the eastern side of Fram Strait, it's warm Atlantic water and H is 0. And you remember I showed you a picture of the ice thickness, and over near Russia, H was less than a meter, so it's kind of thin. So I'm anticipating near this right-hand side boundary, H is going to be much less than 1. So I'm anticipating two different regimes, where the balances are different, a thin regime and a thick regime. Everybody up? Everybody keeping up here? Any questions?
Yeah, if you go back one slide.
Yes.
So if gamma and H are order 1, then the gradient in the x direction has to be order 1, right?
Yes.
Okay.
Yeah. Okay, so now I non-dimensionalize the momentum equations. This is the one with the wind. That's the one perpendicular to the wind. I get three non-dimensional constants. Epsilon, which goes in front of the Coriolis term, is C, which goes in the ocean drag term, and then there's this delta, which goes by the sea surface height tilt term. So if I put in typical numbers for these parameters, delta is order 10 to the minus 2. C and epsilon are both order 10 to the minus 1. And I've chosen my scaling such that H, dx, and tau are both order 1. Okay, so I'm going to ignore the delta terms from here on. No more sea surface height tilt. I'm going to keep these two, C and epsilon, and make an expansion of H, U, and V in terms of epsilon. Right? So I'm going to assume H is some zeroth order quantity plus epsilon times the first order plus higher order quantities. I do the same for U and V, and I'm going to stick those back into my momentum equations and my continuity equation. So I have three unknowns, H0, U0, and V0, and I have three equations, two momentum equations and a continuity equation. Okay, so the first balance is going to be tau and H, simplest can be. So the linear order balance for H is just linear with X, proportional to the wind stress. This is a matching condition to match the thick regime with the thin regime. So this is, given my scaling, assuming H is order 1, this is my leading order balance. So this is my thick ice regime. This tells me that the thickness of the ice is controlled entirely by the wind. There's no thermodynamics in this equation, just wind. If you blow the wind harder, the ice gets thicker. Right? In non-dimensional form, it's order 1. If I dimensionalize it, it's 2 tau, the width of the basin, times this ice strength constant, U star. So if I put in typical numbers for those, I get a maximized thickness of about 6 meters, which is about what you see on Greenland. So that's encouraging. Now, we go to the continuity equation. Remember, I had epsilon in front of the d by dy term, so I ignore that. So this is my leading balance in the continuity equation. U naught, H naught, so the flux divergence along the wind direction is balancing heat loss to the atmosphere. I know H naught, so I can just solve that for U naught. That's what this is here. The velocity in the direction of the wind. So tau is negative. It's blowing from right to left. So U is negative. The ice is moving in the direction of the wind. There's a couple of constants in here, these subscripts with E's. Those are just so I can match the thick ice and the thin ice regime. I'll talk about those in a minute. And then my last equation is the crosswind momentum equation. Now I know U naught here, and I know H naught from the previous slide. So now I know V, the crosswind velocity. So the zonal flow is downwind. That's the thermodynamic equation. So the zonal velocity is balancing the ice formation. The crosswind velocity is essentially a residual between the pressure gradient term, the internal stress term, which looks like a pressure gradient. I'm bringing up my mid-latitude physical oceanography. I refer to that as a pressure gradient. But this is the internal stress term, and that's Coriolis term. So the meridional velocity is a residual between those two terms. The pressure gradient is pushing to the south towards Fram Strait, and Coriolis term, because U is negative, is pushing to the north in opposite sense. Okay? So that's the thick ice regime. Now let's think of the thin ice regime. The zonal momentum balance for that is now between the stress term, or the drag term, ocean drag, C times U, and the wind, tau. So in this case, the zonal velocity is in the same direction as the wind, but it's controlled by the drag, not by the ice thickness. Continuity equation is the same as it was before. So I can just take those two and solve for H naught. Now I'm using the continuity equation to get H. And this beta y is an eastern boundary condition. So at x equals 0, I'm saying as you move along that Russian coast, you're forming a little bit of ice, right? Because you're in the Arctic, you're losing heat, you're making a little bit of ice. I'm going to say it varies linearly with position along the boundary. And then H grows like x to the 1/2, away from the boundary. And then V is determined by the same equation as before, except now, of course, H and U are different. So I didn't write out the whole V equation, but it's still the same thing. So now here, the ice thickness is controlled by thermodynamics. It's coming out of here. And the velocity is controlled by the wind. So it's kind of the opposite of the thick ice regime. Here, if I blow the wind stronger, the ice gets thinner. H goes like tau to the -1/2. And the velocity gets faster. It's just the opposite of what happens in the thick ice regime. So So the dynamics are really very different. So graphically, visually, this is what it looks like. I'm solving those equations over this 0 to 1, minus 1, 0 to 1 domain. I'm blowing the wind uniformly from right to left. I'm specifying h equals 0 right here, and equals beta y. You can see it, little slope in the contours here. Beta y along that right-hand boundary, and then I'm just integrating those equations westward. I somewhat arbitrarily said I'm going to transition from a thin ice regime to the thick ice regime when h is 0.25. I don't really know what thin and thick are, but when h isn't small, I'm saying I'm switching over to the other regime. A little bit arbitrary, but it provides visually a good transition between the two. In reality, I expect there's going to be some region where both the Coriolis term and the drag term are important. But I'm going to assume that that region is narrow. So in the thick ice regime, the gradient is large. This is thick ice over here to the left of that red line. The gradient's large and the ice is thick along the western boundary. The thin ice regime, the gradient is relatively weak and the ice is thin. There's a strong southward velocity in the thick ice regime, whereas in the thin ice regime, it's faster ice and mostly zonal. So the ice is thin and fast over here, blowing downwind. Here the ice is thick and it begins to diverge from the wind. This theory has no boundaries. There's no western boundary here. If you could see, these vectors go right through that somewhat arbitrarily chosen place at -1. There's no normal flow condition there, but still the ice is going to the south. When I first started looking at this problem, I thought, well, the ice is kind of running into Greenland and it's got to go somewhere, so it's going to the south. Now I'm thinking Greenland isn't really the key player. So what's happening here? The ice is getting thicker as it goes to the west because it's got to balance the wind, right? The wind is pushing it up. You need a force to go the other way, and that's provided by the gradient in the ice thickness. But we know when the ice gets thicker, it loses less heat, right? Because it's got to get conducted through the ice. So you can't advect a lot of ice out. Consider a little cell. You lose a little bit of heat. You're advecting ice in. You can't advect a lot of ice out because you didn't lose enough heat to do that, right? So the zonal velocity has to decrease as the ice gets thicker in order to satisfy the continuity equation. The meridional velocity, remember, comes from a residual between the pressure gradient and the Coriolis term. The pressure gradient is constant, right? The HDY is constant. But as U gets slower and slower, the Coriolis term gets weaker and weaker. The Coriolis term was opposing the pressure gradient term. As Coriolis term gets weaker, pressure gradient wins, and it gets southward flow. So it's really a combination of the dynamics and the thermodynamics that causes the ice to turn to the left of the wind vectors. Yes?
When you say pressure gradient, you're not talking about the pressure gradient of the ocean.
No, that's sloppy language on my part. I'm really talking about the stress gradient. And stress is proportional to ice thickness. So I'm immediately mapping that onto my physical oceanography background and calling it a pressure gradient. But you're right, it's a stress gradient that comes from the rheology, which is proportional to the ice thickness. So good, call me on that. I occasionally refer to east and west as well, which I shouldn't do because it's an F plane and the pole is right in the middle. So, yeah.
So Mike, just looking at the plot here, I'm trying to understand a little bit on the eastern boundary condition. It almost seems like that's vital to establishing,
Yes.
further to the west,
Yes.
the north-south ice thickness gradient without its kind of amplification of that.
Absolutely. If I had, in this configuration, if I said beta was 0, so if the ice was thick along, uniform thickness along the eastern boundary, then I would have no DHDY.
And so that you would lose that southward.
I would.
condition.
But I can get the same result if I make the wind a function of latitude, which it really is. So both of those things are going on in reality.
The eastern boundary is that there's a circulation along the boundary that's kind of accumulating. I mean, what's the physical basis for setting that ice gradient, initial ice
Well,
gradient on the boundary?
one, you observe it.
Okay.
But two, imagine you've got some flow coming in at the south.
Okay.
And it's got some kind of a boundary current following along the coast, and you're losing heat all the way along there. So you're making ice as you go along. But I could get the same result if I just made the wind a little stronger here than it is here, which is also true in reality. I don't do that here, partly because it makes the solutions messier. You can write them down, they're just messier. But also, the assumption that d by dx is much larger than d by dy breaks down. If I do both of these things at once, then I'll get solutions, but I'll have violated my assumption in deriving them. Okay, so that's the kind of simple physics behind why the ice is turning to the left. It's because it got thicker. So that's my analytic solution. This is the real world. I would argue that there's some resemblance between these two patterns. Thick ice over here, thick ice over here. Again, this southward flow I do not think is due to Greenland, although if I did have a solid boundary there, I would have some kind of a boundary layer, and I would probably have some southward flow and maybe some northward flow. So there's probably some kind of a boundary layer, and I'll just throw a melt layer or something that sits over there, but I don't need those physics to get southward flow. And in fact, this stuff out here is crossing to the left of the wind vectors well off the boundary. Okay. So I'm being a little bit tricky here, saying I have no boundary in my theory. I have a pressure gradient, or an ice thickness gradient. So it's somewhat implicit that there's something over there that's allowing me to have this gradient supported. It's kind of like a Sverdrup balance for mid-latitude wind gyres, right? The Sverdrup balance assumes there's some kind of a tilt and sea surface height or a pressure gradient, even though you don't explicitly resolve the western boundary. The same kind of thing here. Okay, so let's see if this has any resemblance to reality. I'm going to take a section along this yellow line. There's the North Pole. Now what's over there in the black line is the ice thickness along this section, from here to here. The red line in this half is my theory, my thin ice theory. It goes like x to the 1/2, starting with the observed eastern boundary condition, so the thickness here, and I'm just integrating to the west. So I've assumed a reasonable wind stress, 0.04. I've assumed some kind of a drag coefficient and some change in temperature across the ice. It kind of remarkably falls right on top of the data. And then when I see that the data changes slope, I said, well, I'm going to switch to my thick ice regime. So I do not have an objective measure in this calculation of when I'm going to switch from thin to thick, just that I see that it happens. But if I then switch to my thick ice regime at this point, apply the same wind, apply internal pressure that's representative of what real ice is, I reproduce that gradient as well. So granted, there's some tuning involved here, but the main point is that in the real world, there do appear to be thin ice and thick ice regimes. Okay, so now I want to go a step further in testing some of these ideas. So I presented to you kind of a simple asymptotic theory for the ice thickness and drift. I had to make a bunch of assumptions in order to derive those solutions. I think they're defensible, but they're not obviously valid in kind of real parameter space. So I'm going to take a general circulation model. It's going to be configured in a very idealized way, as you can infer here. This is my Arctic Ocean. This is my Nordic seas, connected by a narrow strait that's somewhat like Fram Strait. The model has an ice model, the elastic plastic rheology. It's got some thermodynamics, solves for ice thickness, solves for ice concentration. It's coupled to the full primitive equation model, the ITGCM. I'm using the model with 10-kilometer resolution. And I'm going to force with an atmosphere. Okay, so I specify 10-meter winds. I specify downward and longward radiation, or downward long and short wave radiation. Calculates the outgoing long wave radiation and turbulent heat fluxes. So it really is a coupled ice ocean model forced by atmosphere. The model is initialized. I've got a 100-meter thick halocline in my Arctic basin, and there's sort of warm, salty Atlantic water everywhere else. The model is forced by restoring the warm, salty water down here. are restored to some fresh water just around the perimeter here in the Arctic Ocean. That represents river runoff and cross-shelf exchange processes that aren't resolved in this model. Pacific water that's coming in through Bering Strait. And it's forced with a wind, which I'll show in the next slide. So these runs are really pretty short. They're like 5 years long. So the model doesn't drift a whole lot from its initial state. So the ocean model dynamics here aren't terribly important, only that I maintain a halocline so I'm not melting the ice from below. So I don't want to dwell on this too much, but there is a fully coupled ocean underneath this. This is my atmospheric temperature, so it's about minus 16 here, and then it kind of warms as you move away from the pole, all the way down to about 10 degrees here. This is my long and short wave radiation, and network downward flux. And the wind is indicated by those red arrows. So not terribly realistic away from the central Arctic. But I did not want to put any curl directly onto the ocean from my wind. I just wanted to see what would happen if I used uniform winds. So there's no Beaufort gyre here, for example. And this is the mean ice thickness and ice drift velocity over the final 2 years. So I'm getting about 6 meters of ice over here. These gray areas are 0, so less than a meter along the eastern boundary. And this is my model's transpolar drift. It's kind of leaving the eastern boundary, turning out, and flowing out my model for Bering Strait. The Beaufort gyre would sit up here. I'm going to kind of ignore everything in the top half of that picture, and I'm going to focus on this transpolar drift light circulation. In this case, the ice is driving the ocean. So if I look at the stress, the ocean is providing a drag, which is what I had assumed. It's possible that the ocean would be driving the ice because I've got wind and buoyancy forcing in here and I've got a full ocean general circulation model. But that's not what happens. It's ice driving the ocean. So that's the numerical model. That's my theory. And again, I would argue that these are qualitatively similar. If you look at the magnitude of the velocity vectors, they're similar. They're about 5 centimeters a second. Over here, the ice motion is pretty slow. And it turns out that this shape of my model domain is somewhat blocking the ice. It's not terribly evident that this strength of forcing, but if I blow the winds harder, it becomes important. Now, and I'll show that later in the diagnostic. So that's something that's not represented in the theory. And that's, again, this real world estimate of the drift, and I think it looks kind of similar. So I want to use the MIT GCM to test some of the parameter dependencies that are predicted by the theory. Before I do that, I want to revisit some of my assumptions that went into the theory, because I can test them in the model. Particular steady, is that really relevant? So this is the picture I showed before, the ice volume. These are diagnosed from the MIT GCM. The black line is my steady forcing, that's sort of this case I just talked about. The red line is one where I put a seasonal cycle on the atmospheric temperature, the wind, and the shortwave radiation. And I get a seasonal cycle. Not quite as large as this one, but still reasonably large, especially the ice export shows quite a large seasonal cycle. The mean ice volume is nearly identical with the steady forcing case, and the ice export is only about 20% different between the steady forcing and the time-dependent forcing. So I'm feeling comfortable that the steady forcing is kind of representing the main physics. These are the mean ice thickness and vectors of steady forcing and with the seasonal forcing, and they're nearly the same. So while I think it's not crucial to getting the basic result. So another assumption had to do with my scaling of the momentum equation. So I'm taking the slice along this red line, and what's plotted here are the terms in the momentum equation. That's the eastern boundary, that's the western boundary along this line. So this is the wind, 0.04 newtons per meter squared blowing to the west. In the eastern basin, the wind and the drag balance. So that's my thin ice regime. In the central basin, it's mostly the wind and the internal stress. That's my thick ice regime. The dotted line here is the tilt, which is indeed really small, except near the western boundary. So it's okay to neglect that. And the Coriolis term is small but not zero. So that's again consistent with my scaling. Now, another big assumption was my ice rheology. I had assumed that sigma 1,1 was proportional to H. and that sigma 1, 1 was much bigger than sigma 1, 2. So this is sigma 1, 1. That's the mean ice thickness. If I plot them as a scatter diagram, the slope isn't quite 1, but they're, it's not bad. There's a pretty close to a linear relationship there. And I don't show it here, but indeed sigma 1, 2 is much less than sigma 1, 1. So I can ignore those cross terms. Okay, so now I want to use the model to test the theory. The length scale of the Eastern regime I can write like this. X is the length scale. H is this thickness in which I'm saying I'm switching from one to the other. If I say 1 meter, somewhat arbitrarily, the theory predicts 450, that should be kilometers, and the model results 460, so that's surprisingly good. The layer thickness I can calculate from this, and the theory gives me 5.5, and the model is about 6.5. So reasonable, but not perfect. Given that I'm a modeler, though, I'm to be suspected of tuning things. This is just one calculation. So, I might have just chosen this one because it looked good. So I'm going to do a whole bunch of calculations. I'm going to vary the wind from 1 to 6 meters per second. I'm going to vary thermal conductivity, vary the ice strength, and the basin radius. All these things come into the theory. These red numbers, are the ones that I use for the central calculation. Now I talk about kappa, which is my thermal conductivity. I could equivalently be talking about the change in temperature across the ice, or effectively the surface temperature of the ice, because they always show up together in the theory. It's always kappa times the change in temperature. So I'm saying kappa, you can think warming surface ice also if you want. So I'm going to show a bunch of these slides. I hope they don't put you to sleep. On the vertical axis is the theory prediction. The horizontal is diagnosed from the model. Each of these different colored symbols represent a different parameter. So wind, strength, ice strength, basin radius, conductivity. I'm also going to show this green star, which is from the seasonally forced model run. And then the size of the symbol represents the magnitude of that parameter. So the small circles mean weak wind, large circles strong wind, for example. So I'm comparing here the maximum thickness, and the agreement's reasonable, except for really this one, and there's a hint that this one is breaking down. That's the one I've been talking about up till now, the central case. So I mentioned that due to that shape of that boundary, it sort of traps the ice there, blocks the ice. That's what's going on here. When I blow the wind really strong, the ice just kind of piles up and it can't get out because it runs into that southern boundary. If I redo that calculation with a straight western boundary, then it agrees with the theory pretty well. But there's other problems with that, so that's why I didn't show that in general. This is the length scale of that thin ice regime. It varies from about 100 kilometers out to 700 kilometers or so. The agreement's reasonable. This is that same problem with the thick ice. We see that the increasing the wind increases the maximum ice thickness and also the width of the eastern regime. The ice strength decreases the maximum ice thickness. Has very little effect on the eastern regime, both in the theory and in the model. The basin size increases the ice thickness. It also, in the numerical model, changes the width of the eastern regime. That is blue squares. The theory says it shouldn't matter. So I don't understand that, but numerically it seems to make an effect. Conductivity has a minor effect on the thickness in both the theory and the model, but it does affect the width of the eastern regime. So another thing we might be interested in is how much heat is lost from the ocean to the atmosphere through the ice. We know H. These are specified, so it's pretty straightforward to get the heat loss. And remember, H has a thin and a thick ice regime. So I can just integrate these up, compare them with the model, and that's the scatter diagram I get. The model produces, on average, a little more heat loss than the theory predicts, but the parameter dependence isn't too bad. So there's an offset. Right? These are a little bit below the line, but they're kind of parallel to the line. So you get more heat loss for stronger winds, because you're expanding that thin ice region, and the heat loss goes like 1 over H. So you lose most of your heat in that thin region for strong winds. Increased ice strength, because that thins the ice in the western. The smaller basin, this is the basin average, so it's just more of it's represented by thin ice. and increasing thermal conductivity. All right, that's the one I just showed you. This is a fraction of heat lost in the thin ice regime, and for most parameters, we're kind of sitting here, and both eastern and western regimes are important. So the volume of ice, again, once we know the ice thickness, we can just integrate it up and get the volume. For most parameters, it's predicted reasonably well. These are, again, that strong wind regime where it fails. And these numbers, 10 to the 12th cubic meters, aren't bad numbers compared to the real Arctic Ocean. Given that I have a funny round Arctic, it's not the same size. We're kind of in the right parameter space. So we get more ice volume for stronger winds, with decreasing ice strength, with larger basins, of course, and increasing thermal conductivity. Now, the last quantity I wanted to diagnose was the ice export through Fram Strait. Remember, in the beginning of my talk, I was interested in what sets the mean ice thickness and what sets the ice export through Fram Strait. So rather than integrating my advection equations, I'm going to get this just from thermodynamics. If I know how much heat is lost, then I know how much ice I have to get rid of because it's in steady state. So however much heat I lost, I make a certain amount of ice and that has to go. So I can integrate that because I know H, and H gives me heat loss and then the formation rate. And it agrees really pretty well. They said the time-dependent case, the ice export was a little different, but by and large, it agrees pretty well. Even in the strong wind case, because most of the ice export is coming from the thin ice regime, because that's where I'm making most of the ice. That's where most of my heat loss is. So I have an error in the thickness of the ice towards that left-hand boundary, but that ice is just sitting there anyway, so it doesn't really affect my ice export very much. Okay, so there's one more thing I wanted to talk about. What can we expect in a warming climate? So I talked a little bit about parameter sensitivities, and I'm hoping that I was able to convince you that my theory is at least consistent with my numerical model. They're both idealized, so none of them are the real world. But the numerical model's got some more complete physics in it, and they both show some superficial resemblance to the real Arctic. So what can these tell us about what we might expect? I think there's two things that are probably going to happen in the Arctic. The wind is going to get stronger, and the surface temperature of the ice is going to increase in a warming climate. So I'm going to apply the theory to predict ice thickness, ice volume, and heat exchange with the atmosphere as a function of temperature and wind stress. So there's three plots here: the maximum ice thickness, the total ice volume in the Arctic, and the heat loss to the atmosphere as a function of the surface temperature of the ice, which remember is a boundary condition in my model. It's how the model is forced, and the wind stress. Now these are all in dimensional units. So the case we've been looking at kind of sat right around here. For very weak winds, the maximum thickness and the ice volume are essentially independent of the temperature of the surface of the ice. That's because we're in the thick ice regime. Remember, when the wind is really weak, the thin ice regime retreats to the eastern boundary, and it's all thick ice. But as the wind gets stronger, we expand that eastern region, and then the heat loss really begins to depend on the temperature, the maximum thickness. Depends on the surface temperature. There's a value right here, by this red line, at which the maximum ice thickness peaks, and then after that it begins to get thicker, or it begins to get thinner. That's because that eastern regime, imagine you blow the winds really strong, the ice gets blown all the way over to the western boundary, and you never enter this thick ice regime. You have thin ice everywhere. So this line, which you can write down an expression for, is telling us we're kind of switching from a thick ice dominated regime to a thin ice dominated regime. You see the same kind of thing going on in the ice volume. It happens a little bit earlier in terms of the wind, but the ice volume also has a peak. The heat loss to the atmosphere does not show a peak. So increasing winds and decreasing surface temperature, so colder surface temperature, both result in more heat loss to the atmosphere. Now it depends. You can have more heat loss if you're moving in this direction. You can have less heat loss if you're moving in this direction, or you can have no change in heat loss. Depends on the relative changes of surface temperature and wind. Now remember when I showed the real world, that section across the mean ice thickness, you could see that the thin ice regime covered more than half of the basin. So that suggests to me that we're on the right-hand side of this red line in these two graphs. So in the future, if we increase the wind or we increase the surface temperature, I think we're going to be seeing a decreasing maximum ice thickness and a decreasing volume and an increasing heat loss to the atmosphere. If we were to the left of that red line, then we might have seen thicker ice. So it's not obvious beforehand, but I think we're probably to the right of that line. Okay, so that's really all I wanted to say. My goal was to just develop the simplest theoretical model I could to understand the basic ice thickness and ice motion in the Arctic. The approach was to just simplify the momentum and continuity equations, toss out what terms I think I could get away with. As a result, we get these two regimes, thin and thick ice. The dynamics of those two regimes are very different. And the basic parameter dependencies predicted by the theory compare well with this general circulation model that I use. And finally, I think we can anticipate thinner ice and less ice volume, more heat loss to the atmosphere in a warming climate. So we've got a few minutes left. I'd be happy to answer any questions.
Questions for Mike, please? Okay.
Just out of curiosity, I don't know anything about this at all, but would the presence of the ice affect the wind speed as well?
It does. And in fact, when I mentioned that a warming climate would increase the winds, part of that is because there's more heat loss through the ice, which provides more of a heat flux at the bottom of the atmospheric boundary layer, which results in more mixing in the atmospheric boundary layer, mixes momentum down in the boundary layer, and accelerates the winds at the top of the ice. So yes, they're coupled.
Have you tried matching the solutions across where thin and thick ice regime are both of the same order of magnitude?
You mean in the theory?
In the theory, yeah.
Yeah, the equations become coupled in kind of an intractable way. So, I match them so ice thickness and ice velocity are continuous, but I don't have a solution where all three terms are important. But numerically, this is from the GCM, this is that region, right? The stress and the drag are both important for a few hundred kilometers. And then the drag decreases and the stress takes over. So we're kind of thick ice here, thin ice here, and there. But there was a paper by Mike Steele some years ago, about 20 years ago, in which he diagnosed these terms, and he found a bimodal distribution. You either had this balance or this balance. Now, it wasn't only bimodal, there was stuff in between, but it kind of stood out as those two regimes were represented in his full kind of kitchen sink GCM.
Yeah, can you put that slide up again where you're looking at the changes of trends or trends on the last
one?
Yeah. So looking at any of those, but say ice volume in the right-hand one, and thinking about future changes in surface temperature of the ice. Right?
Mm-hmm.
So wherever we are now, we're moving upward on that diagram.
That's right, yeah.
But I was, when I think about what do we know about projections for Arctic warming, well, it's always in terms of surface air temperature. What are the projections? Do you expect there to be kind of a 1-to-1 ratio in changes of surface ice temperature?
I think roughly, within the extent that I believe the details of what this model is predicting, 1-to-1 is, I think, a pretty good assumption.
So if we had a 4-degree Arctic, surface air temperature one, stuff be moving up something like 4 degrees on that scale. Or-
The error in that assumption wouldn't be the limiting factor in this projection, right? So yeah, I think roughly that's good enough. But it depends on the energy balance at the top of the ice, right? So you've got incoming radiation, outgoing radiation.
So where are
turbulent
we
fluxes.
in parameter space in that right hand?
Well, I would say roughly here. I think the stress
It's
is
16 degrees and we're around
0.05. I think I used 0.04. So I was blowing the MIT GCM with 4 meter per second winds, and I diagnosed the stress from their air sea coupling and their atmosphere ice coupling parameterization, which is a quadratic drag law. And I think I had 0.04 newtons per meter squared. So roughly 0.05 and minus 15.
So none of this accounts for ocean warming below. Right?
That's right. So if you look at the heat flux from the ocean to the ice, it's 1 or 2 watts per meter squared, whereas these averages are more like 20 or 30 or something. So the ocean's certainly important near the inflow, and I think there's this nonlinearity that I've I've completely ignored telling you about. If we have seasonal forcing, the edge of the ice is moving on a seasonal time scale. And in between that, the ocean's absorbing heat. So I think there's probably some nonlinearities there that I've really swept under the carpet that would come in if I allowed some ocean melting, because it's going to affect where the ice begins to form. That's going to affect the size of my basin. So there's some things that I haven't dealt with here.
Mike mentioned that in this regime, the ocean currents are not driving the ice movement. They
Yeah.
act as a drag.
That may not be true in Fram Strait.
Right, I was going to ask, can you imagine other regimes?
Yeah, I think this theory is going to break down near Fram Strait for a couple of reasons. One, I think the ocean may be driving the ice. 2, there's certainly ice shear there, right? Because it's gotten very narrow. And we're trying to push all this ice through a narrow constriction, and it's rubbing up against Greenland. So I think my rheology probably fails there, and the ocean may be dragging the ice there in Fram Strait. So this is really a little further north than Fram Strait. It would be appropriate. But if I can get what's going, unless it's some kind of hydraulic control, if I can get what's heading toward Fram Strait, I'll get what goes through Fram Strait, because it's got no other place to go.
Other questions for Mike? Yeah.
Yeah, you bracketed the wind speed between a meter per second to 6.
Yeah.
What happens if you go a little bit higher wind, say up to 8 to 10 meters per second? Do you see anything?
Well, at 6, things were behaving differently. I alluded to this boundary effect where things were kind of getting trapped in there. So I didn't go further than that. I think I'd probably want a more realistic basin shape if I were to pursue that, because there is some curvature along the western boundary, but not as much as what I have in my model. So I think my model configuration is going to contaminate, if you will, results at really strong winds. Certainly doable, though, and people with realistically configured models, I assume, can do that sort of thing. I don't know if anybody has, though.
Other questions? Well, thanks.
Thank you.